Okay, so in an earlier clip, previous video clip, we looked at infrared spectroscopy and how we can measure the absorbance of radiation by an atom, compound or molecule in order to identify it or find out how much of something is in our sample of interest. Now we're going to look at emission spectroscopy, so something giving out light and then detecting that light again in order to be able to quantify how much of something is present or find out what is present. And the particular technique that we're going to exploit is fluorescence. So if you're able to see that, when I hold the ultraviolet, so a different region of the spectrum now, when I hold the ultraviolet lamp underneath the solution, it gives a pale blue glow. And this is a solution of quinine. So that's the same compound we find just in ordinary tonic water we get from the supermarket. So quinine is the component that gives tonic water that characteristic bitter flavour. We've got it in its pure form in this solution here, and when we zap it with a small ultraviolet lamp, the quinine absorbs the ultraviolet radiation, an excitation process occurs, and the molecule ends up in an unstable, excited state. So molecules like to be in the most stable configuration possible, and in the case of quinine, what happens is the excess energy is given up, the electrons drop back down to their nice stable ground state, that excess energy is emitted in the form of that pale blue light. So it's a less than 100% efficient process, so we take in UV and we emit blue light of somewhat lower energy. And we have here our fluorescence spectrometer, so this is quite a sensitive instrument, and we can use this to measure the intensity of that blue light as we irradiate our quinine solution at a wavelength of about 350 nanometers. It's all enclosed for safety reasons, so unlike the little demo that I've just shown you, you won't actually be able to see any fluorescence taking place, just to protect eyes and skin from the very harmful, quite intense in this instance, ultraviolet radiation. So we have our sample cuvettes here, and I'm just going to transfer a small amount of quinine into one of our sample cuvettes. So these are precision made for optical reasons and rather expensive. They're made of quartz, so they are transparent to ultraviolet radiation. And if we put our undiluted quinine sample into the instrument, we can measure its emission intensity, so the intensity of this blue light over this region here, 365 to 450 nanometers. So the sample is in the instrument, all I need to do now is click run, and we'll be able to see a spectrum build up which shows the characteristic emission curve over that wavelength range. Our emission intensity curve here, which shows that we're getting maximum emission intensity somewhere in the region of about, I think, 400, 410 nanometers. And it will also generate a data table, and we can process this raw data in a package such as Microsoft Excel in order to be able to do things like construct calibration graphs from multiple measurements, and it shows the actual intensity of that quinine in solution for a particular wavelength. So it's going up in steps of 1 nanometer wavelength, and each nanometer wavelength has associated with it an emission intensity, and we find that for this particular sample our emission intensity is highest at around, I think, 402 to 403 nanometers in this case. If the sample gave an uncharacteristic absorption curve which looked too broad or too flat, we would need to dilute our sample. Fluorescence is a very sensitive technique, so it's quite easy to overload the detector on the instrument. So again, this is just another example of spectroscopy at work, matter interacting with radiation at various wavelengths in order to be able to find out what a particular species is or at what concentration it's present in a solution.